Let's dive into the world of search engine design. This presentation will cover the essential aspects of building large-scale search systems. Search engines are complex systems, but they can be broken down into 4 core components. First, web crawling involves discovering and fetching web pages across the internet. Second, indexing focuses on processing and storing web content for fast retrieval. Third, query processing is all about understanding and analyzing user search queries. And finally, ranking is where we score and order search results by relevance to present the best matches to the user. Web crawling is the initial step in building a search engine. It begins with a set of seed uniform resource locators, or URLs, which are starting points for the crawler. The crawler fetches the content of these pages, extracts new uniform resource locators, or URLs, from them, and adds them to a crawl queue. The process continues iteratively, ensuring the crawler respects the robots (TXT) protocol, which dictates the parts of a website that should not be processed. On the right is some sample code. The class WebCrawler has an init function that initializes a queue and a set to keep track of visited URLs. The crawl function checks if the uniform resource locator, or URL, is in the visited set. If not, it gets the response text from the uniform resource locator, or URL, and extracts the links. Crawling the web poses several challenges. Politeness is critical. It means implementing rate limiting and respecting server resources to avoid overloading websites. Handling duplicate content requires efficient detection and management to ensure the index remains clean. Quality control involves filtering out spam and low-quality content. And dealing with dynamic content means effectively processing pages that rely heavily on JavaScript. Scale is another significant challenge, as crawlers must process billions of pages and petabytes of data across distributed systems. At the heart of every search engine is an efficient indexing system. A fundamental structure used is the inverted index. This index maps terms to the document identifications, or IDs, in which they appear. For example, the term Python points to document 1, document 5, and document 12. The term search points to document 2, document 5, and document 8. The term engine points to document 1, document 2, and document 9. And the term algorithm points to document 3 and document 7. This structure enables very fast keyword lookups. This process transforms documents into a searchable index. The code sample here defines a function called build_index that takes documents as input. For each document identification or ID and content pair, it tokenizes the content, and for each token, it updates the index, creating a list of document identifications or IDs for each term. The index builder has to be efficient to process millions of documents and must support real-time updates. Query processing is the pipeline that transforms a user's search query into a format that can be effectively used to retrieve relevant results. The first step is parsing, which involves extracting keywords and operators from the query. Next, normalization includes stemming, lowercasing, and removing stop words. The third step is expansion, where synonyms are added and spell correction is applied. Finally, the execution phase searches the index and retrieves the results. For example, the input Best Python Tutorials gets processed into Best Python Tutorial, along with the synonyms good and guide. Ranking algorithms are crucial for determining the order in which search results are displayed. Google's PageRank is a well-known algorithm that measures the importance of website pages. The PageRank of page A equals the quantity, 1 minus d divided by n, plus d multiplied by the sum of the PageRank of page T, divided by C of T. Here d is the damping factor, typically 0.85. N is the total number of pages. T is the pages linking to A. And C of T is the number of outbound links from T. This means that authority is equal to the quality plus the quantity of links. In addition to PageRank, other ranking factors include content relevance, the quality and quantity of backlinks, content freshness, and user engagement metrics such as click-through rates and dwell time. A search engine's architecture is typically divided into three main layers. The front end is the user interface where users enter their queries and view the results. The query engine processes the queries, retrieves relevant documents, and ranks them. The storage layer is a distributed system that stores the index and data. Important metrics include indexing over 100 billion pages, processing 8.5 billion daily searches, and maintaining a response time of under 200 milliseconds. Caching is essential for maintaining performance in a search engine. Different layers of caching are used. A query cache stores popular search results. An index cache stores frequently accessed index segments. And a content delivery network, or CDN, cache stores geographically distributed content. The sample class query cache shows how caching can be implemented. The get function first checks if the query is in the cache. If it is, it returns the cached results. Otherwise, it queries the search engine, stores the results in the cache, and returns them. A good caching system can achieve a cache hit rate of 85% and a response time of less than 50 milliseconds. In summary, designing a search engine involves several key components. Crawling is about discovering and fetching billions of web pages. Indexing focuses on building inverted indexes for fast retrieval. Query processing involves understanding user intent and search queries. And ranking is about scoring results using PageRank and relevance. As a key takeaway, search engines combine distributed systems, machine learning, and sophisticated algorithms to deliver relevant results in milliseconds. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.